Okay, so we were talking about fluids. Well, condensed matter at least, liquid and solid. So we went over the heating curve here, how each section of the heating curve calculates heat in a different way. For the total heat of the curve, and someone remind me why the flat parts have heat energy going in, but they're not increasing the temperature. Changing phase. Changing phase takes energy, so those sections are receiving energy, but they're staying the same temperature. Once this new phase has been established, then the temperature will start increasing to the next phase change. All right, so we're going to start talking about intermolecular forces. The people who are not math people like this chapter, because this is more like, hey, here's some concepts, learn them. Now, I don't think the math is hard in this semester with chemistry. However, I will tell you we're coming up to some chapters where it's going to be pretty intensive. So just kind of wrap your mind around the fact that that's going to happen. And please don't be like the student I had one time. He was a senior in pre-med. He's taking physical chemistry from me. And I swear, I thought this accent was a joke that they did for movies. He was like long blonde hair. He rode the long skateboard all over campus. He did, seriously. He was in the back there. He raised his hand, and I go, "Yeah." He goes, "Dude." I was like, "Oh, that's a great way to start." And he goes, "This class is all math." I go, "Yeah, it's statistical thermodynamics." He goes, "Yeah, but I'm going to be a doctor. I don't need math." I was like, "Oh, God, you're in a lot of trouble. You're in a lot of trouble." So I looked at him, I said, "Please at least learn enough math to be able to calculate the amount of malpractice you're going to need." And then his buddy tried to convince me the earth was flat. Well, so that was an interesting day. That's the guy who told me if the earth was round, the bottom of shoes would look like this. I'm like, if the earth had the diameter of a basketball, what? So, intermolecular forces. Now, this list here actually at the bottom is your weakest force and the top is your strongest force. So you can follow that. So, your intermolecular forces are going to be electrostatic in nature. Does anyone know what electrostatic means? So there's two types of things, electrostatic, electrodynamic. You remember what dynamics are in science? So kind of, yes. So dynamics are going to all be based on time, and it's the evolution of a system over time. So a system that can change. An electrostatic system is one, pretty much where we're taking a snapshot. We're looking at what's happening at a single moment in time, or you have a system where you have electric charges that are pretty much stable the way they are. Okay. The first thing we want to do is start to understand the concept of a dipole. That's not good. No, we're still online. There it goes. Okay. What? Wow. Okay. So we're going to be a little laggy. Yeah, dipole moment. Now, how much did you talk about polar molecules? So this is going to be lots and lots of fun. Okay, so one of the things you have to keep in mind, we can't have overall polar molecules. The geometry, you've been talking about geometry. The geometry of the molecule is going to help you dictate and decide if a molecule is polar, because what you're going to start doing is you're going to look at the polarity along each bond in the molecule. You have to start there. You can't get, eventually certain molecules are polar. Now this will be fun for you, all of you can take biochemistry. You have a lot of carbon structures in your body with carboxyl heads on. So it's going to be a COOH group. Gotcha. That's your C double bond O, and then your hydroxide. That's a carboxyl group. Now, that head is polar. And so if the carbon chain is short enough, it's a polar molecule. However, when you start getting to like your lipids and your fats, there's a very long carbon chain. And those are referred to as non-polar molecules, even though they have a carboxyl head. So there is going to be a crossover where when the carbon chain is long enough, the carboxyl head provides such small polarity that it doesn't even matter. Now, the first thing we want to do is understand the notation. So here is, this is what we're looking at. This is like the dipole moment on a carbon-oxygen bond. And the best way to think about it is you can think of the back of it as positive. You're always going to place that cross end of the arrow towards the positive side, and the arrow points towards the negative. Now, so you can kind of see, you can see oxygen in here. You have carbon over here. Has anyone ever seen a map like this? Yeah. You ever seen anything like that? No, that's called an electropotential map. You can calculate them, you can look them up. Electropotential maps are also going to help you understand polar bonds and polar molecules, because the way they do is, like, as they go from blue to red, you go from positive to negative. So you can actually see where most of the electron density gathers on the molecule. For carbon monoxide, why do you think the oxygen side is negative? Why are electrons pulled that way? Yep, it's electronegativity. So the oxygen is going to pull electrons towards itself. So what this does is it ends up leading us to one of our intermolecular forces, or dipole-dipole interaction. So you have a liquid, and solids are going to line up due to electrostatic forces. Like ice, when it forms, it lines up along hydrogen bonds. So the water molecules are going to arrange themselves to hydrogen bond to hydrogen to oxygen, so on and so forth. But your dipole-dipole interactions, imagine a fluid, or this is carbon monoxide, so it could be a gas, but it still works here. It's just, we want to make sure that in this chapter, we're predominantly talking about condensed phases. So you can see the way it works here. You have all these polar molecules. Now, dipole-dipole interaction has to occur, and this is one of the keys, it has to occur with permanent dipoles. That'll be more clear as we go along. Like your carbon monoxide is a permanent dipole. And so what they're going to do is you're going to have you're going to have positives attracted to negatives. And then of course negatives will repel, positive will repel. And so the way dipole interaction works is these molecules are going to move around and end up arranging themselves in the way that maximizes electrostatic attraction. So positive to negative. Okay. So stuff like this is why you can study a fun thing in the lab called Brownian motion. Because you see just a fluid sitting there and you're like, it's not doing anything, but you put some little particles in it and they start jittering, moving all around. Well, that's because the molecules in the liquid are moving around. Okay, let's see here. Okay, a couple of molecules here. What is NH3? That's ammonia. Those of you who have to take standardized exams in the future, you're going to see bigger ones like this. CH3COOH. What is that? It's a carboxylic acid. First off, can you see the carboxyl head on it? Oh, kind of hard to see the atoms, but you see the C double bonded OH? That's your carboxyl head. So this is a carboxylic acid. I have to prepare lunch for everybody sometimes, put this acid all over the food to see if you eat it. Sticky or something? Oh yeah, it's real sticky. I think so, just, well, that depends. Some of you probably ate it today. What is it? Vinegar, acetic acid. Mm. The one on the end, everyone who uses beauty products use that one. It's real fun. It's real fun in organic chemistry lab. You're not supposed to, but everyone always ends up spraying their hand with it. Your hand gets really real cold. CH3, CO, CH3. Huh? Nope. Think nail polish remover. Acetone. So when we're it's easy to see from the map that these are polar molecules. Well, let's start to figure out why. So first thing we want to know is if the bonds in the molecule are polar themselves, because that's going to affect things. So what we have here is you're looking for bonds that have a different electronegativity difference between 0.4 and 2.0. Those are going to be polar covalent bonds. Anything below a difference of 0.4, they're just balanced covalent. Anything above like 2.0, 2.1, you're going to have ionic. So, what are some of the bonds that we have in here? Well, we have a CO bond. And I gave you a small periodic table down here with electronegativities on it. So you notice that carbon, let's see, oxygen is 3.44. Carbon is 2.55. So that's going to give you 0.89. So all carbon-oxygen bonds are polar. What's a color that would show up? I think that'll work. So if we go through and look for carbon-oxygen bonds, we're going to have one there. That doesn't show up real well, does it? Oh, no, it's okay. We'll have one there. We'll have one there. Okay. What other kinds of bonds do we have in here? We have carbon-hydrogen. You find the electronegativities. And so, let's see, carbon is 2.55, hydrogen is 2.20. You get a difference of 0.35. So the carbon-hydrogen bond is not polar. And so if you think of all the places you have carbon-hydrogen bonds, that's not going to provide to the polarity of the molecule. Let's see. Nitrogen-hydrogen. 3.04 minus 2.20 is going to give us 0.84. So nitrogen-hydrogen bonds are polar. This just didn't show up the way I wanted it to. Let's see if that works. Yeah, but it's nitrogen is white. No, those won't do it. Let's see if that works. Okay, so the negative hydrogen. What side's going to be more negative, the hydrogen or the nitrogen? Nitrogen. So boy, this just is not working great, is it? Let me try this color. So all of your, oh, that's a little better. Okay. And you have a nitrogen hydrogen back there. So all of your nitrogen hydrogen bonds are going to produce dipoles. Let's see, there's also an OH bond. That's going to give you an electronegativity difference of 1.24, so quite polar. Okay, so you can start to get an idea of why these molecules are polar. So first off, the ones with only one dipole, so like your acetone, you have that one single dipole sticking up there in space. It's just going straight up. You're not getting any polar contribution from any of the carbon hydrogens. Of course, any two atoms that are the same, that's going to definitely be nonpolar. If I have that one single dipole sticking up into space, well, yeah, that's definitely going to be polar. The others, I'm going to tell you what it is. We won't do it until you get to physics. I actually did it with the students the first year. And some of them honestly thought about changing their careers. So to figure out if a molecule overall polar, what you're looking at is a sum of all the vectors. So you're looking at a vector field of dipoles, and you want to add them all together, and if you end up with anything other than zero, you will polar bond. You'll work with vector addition in physics. But like you can kind of eyeball it. So like look at the ammonia. Do you notice how all those are pointing slightly upwards? You have no arrows pointing downwards to cancel out any of the up. So you know that you're going to have an overall vector pointing up towards the nitrogen. So that's why you end up with a polar molecule. So you can kind of look at them and start to judge whether these are polar or not. All right, hydrogen bonding. So this is it's a special kind of dipole-dipole interaction. It's much stronger than your standard dipole-dipole. And what you're looking at here is hydrogens are going to electrostatically bond or be highly attracted to negative regions on, say, your hydrogens are going to be attracted to like your lone pair regions on your oxygen. Now, this can only happen if your hydrogen is bound to a very electronegative element. So your hydrogens will be down to an oxygen, a nitrogen, or a fluorine. Okay, so right now, those are the three we're working with. Hydrogen bound to anything else, we're just not going to get enough energy, electron separation to form a hydrogen bond. Now, has anyone seen these little symbols before? Your delta positives, delta negatives. Do you remember what they are? Partial charges. So we're not actually calculating a number. We just know that when we have a polar region, the side that's more electronegative will be partially negative. The side that's less electronegative will be partially positive. What we're doing is we're labeling the positive and negative regions of a polar region. And so you see here in water, you have the hydrogens attached to an oxygen. That's one of our atoms that works for a hydrogen bond. And so you're getting so much electron energy pulled towards the oxygen that you get this really positive region on the hydrogen. And so you're going to get a very strong electrostatic attraction between the negative regions on the oxygen and the positive hydrogen. And they're going to start to lock in place. So it is a dipole-dipole, but it's a lot stronger than standard dipole-dipole. Let's look at some more hydrogen bonding. Of course, it's going to lag. Well, we'll look at this in a minute. Yeah, I thought that was fun. People are even starting to not remember where that's from. Yeah. That's good. Okay, here we go. Okay, so on the top left, can anyone tell me what that molecule is? U2H5OH. Or their ethanol molecule. So you look at these, so this is kind of like starting to judge what intermolecular forces are at play. So here I see two molecules where I see hydrogen bound to an oxygen. I know I'm going to be able to have hydrogen bonding going on. If I have hydrogen bonding, do you think I'll have dipole-dipole? Yes, I have to label both of them. There's another one we haven't gotten to yet, but and I see this every year, and then people don't do it. There's one that every single compound, no matter what it is, it has this type of, it's called dispersion forces. Right? You put on there, everything has dispersion, and people will not write it down. And that's the one you should get automatically. Now, of course, you see water doing its hydrogen bonding. Let's look at some of these others. Look at the hydrogen bonding between carboxyl groups. You can get a dual hydrogen bond between two carboxyl groups. And then look at some of the hydrogen bonding with amine groups. The amine groups could also hydrogen bond to each other. So two amino acids could hydrogen bond. So that's actually something that happens in the DNA helix. In the center, hydrogen bonds are holding the helix steady across the gap. And so you'll have a hydrogen, so it's usually a hydroxyl group. And then on the other side, you'll usually have a nitrogen. And so and they lock in place. Now, dispersion forces. I put in the full name. I don't care if you just write okay. I don't care if you just write dispersion, you can do that. I put the full name in because again, standardized exams, sometimes they'll go London dispersion forces, but I want you to know that they're the same thing. So remember, all molecules do this. So if you're labeling intermolecular forces, this one's automatic. Okay, so what happens is, so up at the top, you have these neutral compounds. Now, electrons in a molecule are not static. They're kind of like a cloud or a fluid. They're constantly moving and shifting around. We've already talked about, for example, resonance. Now, resonance is actually happening in the electronic structure of molecules. So they're constantly moving around. So you're going to get these things called instantaneous dipoles. So this neutral molecule will momentarily get an imbalance in its electron, and you'll get a positive and negative region. Well, now that that's unbalanced, it interacts with another molecule, forces its electrons to be unbalanced, causing an induced dipole. And now that they're both temporarily polar, they're going to start displaying attractive and repulsive electronegative polar. And so what happens is this happens over and over and over and over and over again, until eventually your molecules just kind of spread out and spread away from each other. And that's called dispersion. Oh, it actually went this time. Okay. So as far as induced dipoles go, well, instantaneous dipoles, let's start there. It's easier for instantaneous dipoles to occur on larger atoms. So, I mean, if you look here, the larger the atom gets, the further out from the nucleus the electrons get, the more they're just going to kind of slosh about. So the electrons on smaller atoms are held much tighter by the positive nucleus, so they don't move as much. So yeah, you're going to get induced dipoles and instantaneous dipoles a lot easier on bigger atoms. And so let's kind of think of how intermolecular forces affect affect experiments or reality. So if you look here, you see all of our halogen. So like all of our halogen standard molecules. So your F2, your Cl2, Br2, I2. Look at the boiling points. Can you explain those boiling points? See, the fluorine boils at very, very cold temperature. So it's a gas automatically. And fluorine's a smaller atom. Why would it be easier to boil the molecule that has smaller atoms? The electrons in there don't move around as much. Well, let's put it this way. Let's look at the bigger ones. If the electrons move more, am I going to get stronger or weaker dipoles? Stronger. Your larger atoms produce stronger dipoles. Stronger dipoles produce stronger what? Well, so think of it this way. If I have a charge that's a +1 and a -1, and those are attracting each other. But then I have a charge that's a +3 and a -3. Are those attracting each other less or more? More. So these molecules with the larger atom producing stronger dipoles or more pronounced dipoles, they're going to attract each other a lot more strongly than say like your fluorine. So the fluorine electrons will barely move. And so when you have this stronger intermolecular force, this stronger electrostatic attraction, then it takes a lot more to break those apart from each other and boil into the gas phase. And so in this case, the stronger intermolecular force, the stronger dispersion, is causing the boiling point to go up. I would ask you about Coulomb's law. Has anyone ever seen that? You don't get a play, I know you've seen it. Coulomb's law. Okay, it's a way you can judge. I would actually learn it. It's a way you can judge the strength of intermolecular forces. It's also going to be a way to judge lattice energy for crystals. It has to do with the electrostatic force of attraction between a positive and a negative. It can also be a repulsion, but we'll just take attraction for now and work with that. All right, let's look at these three molecules. Take a few minutes and try to tell me what intermolecular forces are at play. Can you name that one? I can. There is. How many carbons does it have? And I'll tell you, everything is single bonded. You can tell that by the number of hydrogens. 5 carbons as well. Pentane.
Yeah, what do they do?
Why
do they not why not like C5?
You can also do it that way. This is constructs like this start to give you they're supposed to give you a map onto what the molecule actually looks like when it's in its bonding. So like it's Lewis structure. So yeah, so you have methyl groups on the end, then down the center you have the other carbons. You have hydrogen up and down, hydrogen. Yeah. Mm-hmm. So this is kind of more like a map on how it bonds, on what it looks like.
I get it.
You'll see this a lot in organic chemistry.
I got it.
So what we have dipole-dipole, we have dispersion, we have hydrogen bonding. Just work with those three, see what you get. Dispersion, dipole-dipole, and hydrogen bonding. Work with those.
So you see
they're going to, because well, no, that they won't. Look at C. Look at C. Yeah. How? So do you remember what you've seen? You've already seen that molecule in letter C. Do you remember what it is? Yeah, it's not. The hydrogens are attached to the carbon on that one. That one's formaldehyde. So part of this is learning how to figure out the structure of the molecule. Now you will have hydrogen bonding on B,
Yeah.
because again, you see structurally, you see the hydroxyl group at the end. So you know that that's going to be an OH.
The first one's wrong.
Nope. What do you think the first one has? It does, it automatically has, they all have that. So we're gonna go with that. Does it have hydrogen bonding? No, why not? Right, the hydrogen has to be bonded to a nitrogen, oxygen, or fluorine. You don't have that. So no hydrogen bonding. What about dipole-dipole? Nope. No. So remember, I told you that dipole-dipole depends on permanent dipoles. That is not a permanently polar molecule. Plus, remember how we said CH bonds are not polar?
Right.
There's no polarity in that at all.
So that means they're keeping. It's just
Right.
under.
Yep, it's only dispersion.
Okay.
The second one.
Does because of that.
Right, so now, of course, we have dispersion. We know carbon-hydrogen bonds are not polar, so that carbon-hydrogen region not going to contribute. This is a small enough carbon chain that, yes, the hydroxyl group does create a polar molecule. So it's permanently polar, so it's going to be dipole-dipole. And I'm not going to give you any molecules where you have to guess if it's beyond the polar region. If I give it to you and it's like it has the hydroxyl group there, it's going to be polar. That's all of it. Yeah, that one is all of it. That one is dispersion, dipole-dipole, and hydrogen bonding. Now, the next one, that one, don't let that one trick you. You need to figure out what that looks like as a molecule. H2CO, that's formaldehyde. Are either of those hydrogens on the ion?
I think it's
No. So hydrogen bonding
because C that holds.
right. The CO bond is very polar. And so it's dipole-dipole and dispersion. Little more abstract in the math, but you pick it up as you go along. Now, since we're actually in Chem 2 material, let's see if you can answer some standardized, some ACS test questions. I told you we would practice these throughout the semester, so you're more used to that exam when we get there.
Yeah, I can't play those for me. It's H2. It's the water molecules and part of that.
Well, that's the geometry. Remember hydrogen bonding. So remind yourself of what. So we're going to discuss the words. Remind yourself of what intermolecular means. We're going to discuss intermolecular and intramolecular. So yeah, so inter is between two molecules. Is what? It is.
Wait, what is all the water stuff?
So those hydrogen bonds are so strong, it's going to spike the boiling point.
Oh, wait, so it's wait, why?
Because again, the intermolecular forces, the hydrogen bonding, is going to affect, that strong intermolecular force is going to drive the boiling point up.
But C is also that.
No, because the shape of the molecule has to do with intramolecular force.
Oh my God.
See, that's why I want to practice these throughout the semester, because these exams, they love to throw stuff at you going, did you really read it? And I hate that. So like, fine, we'll just practice it.
Except for like say.
Well, and hydrogen's not as combustible as people think. Let's look at the second one. Which of the following would have the lowest boiling point?
Give me.
Think of all the intermolecular, the more intermolecular forces you have, the higher the boiling. Where's your contents? We're not trying to give you weird look, I just can't say it yet. People say this. We're gonna get you to the point where you're just gonna give an answer no matter what you're like, I'm right, but that's not, no, I'm right. That's what we're gonna get you with.
See, if there's like, Wait.
There are the fewer intermolecular forces.
So it's like- Let's see.
Who thinks it's D? You would be correct. So, the reason is, well, first off, larger atoms, the sulfur, you're gonna get a stronger dispersion. Hydrogen bonding, that's automatically out. Hydrogen bonding is automatically out. Hydrogen bonding is automatically out. This is a molecule where you have a nitrogen bound to a nitrogen. It's not, it is the most nonpolar thing to get. Oh, you'll still get some dispersion, but very little. And nitrogen is at the top of the periodic table, so it's a smaller atom.
How's there,
Okay. Now, there's two more, and we're not really gonna work with these too much. I just want you to know they exist. So dipole-induced dipole. So again, this kind of goes back to the dispersion forces. So again, the dispersion, remember, started with two electrostatically equivalent molecules, where then one had a momentary, well, I lost the word. It was a momentary dipole that induced a dipole in another molecule. Okay, so temporary dipole, that's it. This one is different because you have a permanent dipole that comes in and forces a dipole on another molecule, and then those are going to interact. Okay, so that's the slight difference. This one is a permanent dipole affecting a nonpolar molecule. The dispersion is a temporary dipole affecting a nonpolar molecule. And then this process here, the ion-dipole interaction, that there is called hydration. So hydration is when water molecules come in and with their electrostatic regions, they take apart a crystal. So in this case, you see it pulling apart hydrogen, sodium chloride, so table salt. And you notice how they line up. So the sodiums, all the negative regions of the water are going to rotate because of sodium. All of the positive hydrogens are going to rotate because of chlorides, and you get these nice little bubbles. And this ion dipole is the strongest intermolecular force. Now, talking about physical versus chemical changes. Remember, so when you're looking at this, so example, your phase change, that's a physical change because it's carbon dioxide before, it's carbon dioxide after. It just changes from a solid to a gas. It's a physical change. A chemical change involves a change of the substance itself. So here we see, so this is something to learn. This is a very standard combustion equation. All of your combustions are their standard reaction. We're going to follow a very similar pattern. So here we see a hydrocarbon with oxygen. Combustions are always going to have oxygen. And when you combust a hydrocarbon by itself, your only products, you're only going to get carbon dioxide and water. Those are always the products for a hydrocarbon and water. But here you notice that the combustion takes ethanol and oxygen and turns it into carbon dioxide and water. That is a change of the substance itself. That is a chemical change. Okay. So not that difficult of a concept, but it can trip you up if you're not paying attention. Just make sure you remember physical change versus chemical change. And I'm guessing we're about out of time, aren't we? Okay, well, we'll continue on from here next time.